All right, hello everyone. Welcome to our last intro to tech of the semester. We're here to bring you machine learning by Clarice, one of our previous officers. She's really good at all that stuff, more than I know. Here's the check-in link to get you all the event credit. Again, you can get invited to our banquet at the end of the year to get a free stuff and become a member with us. And looks like I'll let everyone scan the QR code around now. Yes, this is where you learn about machines.
Just everything about machines.
Everything about machines.
Everything and anything. Maybe.
Can I not write my code for optimal control? Dude, nonlinear problems are not fun.
All right, everyone seems to be good, and again, thank you, Clarice, for coming out, and the shows are yours.
All right. Just give me this. Okay. So, just kind of like show of hands, who here has experience with machine learning? Or okay, there's some. There should be a hand right there. Okay. So, like I said, this is gonna be an introduction. I hope that. Oh, okay, it's not letting me present. Oh, okay. Okay, so I hope everyone can learn at least something here, some new material. If there's anything you guys want me to explain any further, also just stop me at any point to ask. But this is kind of the general agenda of what we're going to be going over for the next hour. So machine learning is really diverse and varied topic, so it's really hard to try to squeeze it all into an hour. There's a lot of things that I'm definitely going to leave out, but that's just the nature of a topic like this. So first off, we should start by defining what machine learning is. And bare bones, if you just look at it, it's just extracting knowledge from data. So getting information from raw data and trying to find any kind of patterns within it. So machine learning algorithms, again, one that's going to be learning from any data, any input that you give it. And then if you kind of look at this diagram here, you can kind of see like the workflow that you have when you're working with machine learning. So you're going to have a problem and you're going to try to solve it with a model, and you're going to go through a lot of iterations. It's hardly ever going to be perfect on the first try. I think one of the things with machine learning is that it's very much an iterative process where you're just constantly going through and trying to improve your models. So let's talk about some applications first for machine learning. So one of the big ones is going to be healthcare. So you can use it for diagnosing and personalizing treatment. So if you're looking at like past patient history. This example here is specifically for tumor detection. So that's using a method called semantic segmentation, where essentially you're just looking at pixels and trying to identify each pixel, which is perfect for tumors because you want to see where they are and how big they are. Another one, finance. So that's going to have to deal with like trading, risk management, even your credit scores. So for example, detecting credit card fraud is a big one. So that's using anomaly detection. And that's just trying to find anything that's outside of the norms, anything that deviates from that. And then lastly, business. So this is another big one where you're trying to find how can I improve my business? How can I make better decisions? So for this example, you can use machine learning to predict how much a company is going to make in the next year. So that can be using past year's revenue information or even other like factors that the company is changing. So to kind of start with key concepts, I only put 4 here. There's definitely a lot more, but I think these are at least the 4 most important ones to know if you're about to start any machine learning model, and it applies to all of them. So the first one is going to be features. So these are all of your input variables, and it's anything that can influence what that output is going to be. So for examples, I put like temperature and age, but if you want it within a context, for example, in the demo, we're going to be going over predicting housing prices. And so in this case, the factors or the features that we're going to be looking at can be the number of bedrooms, square footage, number of bathrooms. So those would be considered features for a machine learning problem. So for the next one, it's going to be labels. So this is what we're actually trying to predict with our model. So in the housing example, that's going to be the price of the house. Or for example, I also put categories up there so if you're doing some kind of like image classification, it could be the different images you're trying to classify, like if it's dogs and cats or like different kinds of flowers or something like that. And then the next ones go hands in hand. So this is going to be your training and your testing data. So with any model, you're going to have to initially train it so that it can find those patterns and it can find those different features that are going to be important in your prediction. So typically, when you have a data set, you're going to want to split it into training and testing. So once you train it, then you can go in with your testing data to evaluate how well a model is performing. And so this is because you don't want to show the model any old information that it's already been trained on. You typically want to use new novel data for your testing so that you can see how well it actually works. So going in, let's talk about different types of machine learning. So like I said, it's a really broad topic and there's a lot of different kinds, but these are the three main ones that you're going to find. So with the first one, you have supervised learning. So this is when you have a data set and your data is already labeled in there. So for example, with the housing prices one, you give the data and the prices are already there. You're not trying to predict what those prices are. So what you're trying to do is just map any input to predefined outputs. Meanwhile, with unsupervised learning, your data set is not labeled in this one. You're letting the model try to figure out what those groups are within the data. So you're not giving it the actual explicit labels. So for example, like think about your iPhoto library. If you've noticed that sometimes it starts to group pictures of the same people together and you don't necessarily tell it who those people are, but it's able to see like, oh, this is one person. It starts collecting all their photos together. So that's like an example of unsupervised because you didn't tell it who that person was, but it already starts like getting familiar with who the people are. Another one is reinforcement learning. So this one is a little bit harder to contextualize, but you don't have explicit data involved with reinforcement learning. It's more you have an agent interacting with an environment. So think of playing a video game and you're a character within that game and you're trying to essentially get more points. So you're maximizing rewards in this scenario. So you're trying to go through the game trying to figure out what's going to get you the most points or what's going to maximize your rewards and what actions are going to take away those rewards. So I know I talked a lot, but here is kind of like some diagrams to talk about it. So if you look up at the supervised learning, you can see that in this example, your labeled data is shapes, and then you also feed it labels which tell you what the shape is. So it goes through the model, and then when you start testing it, you can see that it doesn't explicitly give it what those labels are. So the model has to predict what shape that is. Meanwhile, for unsupervised learning, you'll see that there are no labels here, but you can see that there's two very distinct groups here. Even if you don't know what those groups are, you know that there's at least two distinct ones, which in this case is going to be apples and watermelons. And then lastly, you can see your reinforcement learning. So over here, you have your agent interacting, in this case, with like fire, and it knows that interacting directly with it is going to like reduce its reward. So next time, it can learn to avoid it. And then something else that's also, I feel like, important to talk about is the difference between machine learning and deep learning. I feel like a lot of the time the terms are used interchangeably, which is not necessarily wrong, but there is a difference between the two. So with deep learning, the reason why it's called deep is because this tends to refer to specifically neural networks which have multiple layers. So that's what's making it deep. So the main difference is that deep learning tends to also use a lot more data, and because there's more layers to it, it's also more computationally intensive. Meanwhile, machine learning, like I said, it's a lot broader. But again, deep learning is machine learning. It's just a subset of it. Okay, so there's a lot of different algorithms, but I feel like it's just interesting to look at what some of the different ones are. So like I said, we have our three types of learning. So some examples of supervised learning, and I feel like some of you guys have probably heard of these before, like especially linear regression, even outside of the context of machine learning, you probably learn it in math. So linear regression is an example of supervised. K-nearest neighbor, so you can see that there's different classes here. And then random forest is also a machine learning algorithm. Some examples of unsupervised learning is this one's called k-means clustering over here. Like I said, you don't necessarily give it what the labels are, but if you see that there's three distinct clusters here, and the model is going to try to find where those distinctions are. And then this one, PCA, principal component analysis, this is for if you're dealing with higher dimensional data and you want to bring it down. So I know I kind of breezed through that pretty quickly, I realize now, but is there any questions at this point before I start moving into more of the demo? Nope. Okay, cool. So for today, we're going to be using Python, and we're going to be using Colab. I know a lot of people also talk about using like R for different kind of data or even machine learning tools. I've used it before. I personally prefer Python. I just feel like it's easier to work with and more, it's just preference at this point. And then I also have, like I said, we're using Colab today, but I know a lot of people like also using Jupyter Notebook. It's a lot nicer when coding in it. Okay, so I'm gonna go ahead and go straight into the demo. So like I said earlier, can you guys see this? Yeah, okay. So for the demo, we're gonna be going over linear regression. I know it's one of the more simple ones, but I think it's a good place to start if you're just trying to get familiar with what makes a machine learning model. So in this case, like I said earlier, we're going to be trying to predict a house or the price of a house based on a lot of different factors. So for this one, I grabbed this data set from Kaggle. Kaggle's really great if you're trying to just practice. They have a lot of data sets out there that's pretty much like already formatted for you if you want to try different machine learning tasks. So this first block here, all it's doing is just connecting to my Google Drive just so I can access the data set that's already loaded in there. And then onto libraries. So there's a lot of different libraries you can use, but for the purposes of this demonstration, we're just gonna focus really on scikit-learn. We also have like pandas and numpy and matplotlib, but that's just to kind of help us format our data. Okay. So starting off, we're just importing our data set. Here I'm just showing like it's good to always look at your data to make sure you know what's inside of it before you really start working with it. One of like the most important parts before training models or even starting is cleaning your data and getting it. Because in the real world, you are rarely ever going to find a clean data set. There's a lot of like looking through data sets and then having to format it. And if anything, I always find it's the most time consuming part for me, which I really, really hate, especially if it's not like in a format that you can work with directly. So you have to go through a bunch of like transformations. But just to start with, you can see that we have price at the far end. That's going to be our label. And then everything else to the right of that is our features. So that's going to be area, number of bedrooms, number of bathrooms, how many stories there are. And then these next ones, is it near a main road? Does it have a basement? Is there air conditioning? And then how many parking spots are there? So that's like a fair amount of features to look at. And then here I'm just showing like the last few lines. There's a lot of different ways you can see like how your data is shaped. So like if you're just calling the tail end of it, you can just kind of see how many records you have. In this case, we have 545. And then this is some more different ways to kind of look at the format of your data. So, because sometimes you'll find that some of the NumPy like functions require your data to be formatted a certain way. So it's always good to look at what shape it actually is in to make sure that you can feed it to certain functions. But in this case, data.info is also really good because it can tell you exactly what the column names are. It can tell you if you even have any null cells in your data sheet, which is important because sometimes you're going to find that you can't work with null data, so you have to, like, that's another part of the data cleaning process, is that you're going to find that you have to fill those nulls with either like zeros or like the mean or the average. And then it also tells you the data type. So, like I said, it's always really important to be familiar with your data before you start working with it, just so you know if you run into any issues, you know exactly where those issues might be coming from. Okay, and then like I said, data cleaning, really important part of the process. So in this case, there's not a lot initially that we have to clean with our current data for it to work for linear regression. But one of the big things that we have to do is we have to change, do you see where it says like main road, basement, air conditioning? You notice that these aren't, this isn't numerical data. This is like a binary. And so that doesn't work for linear regression because you need all numerical data to feed it in, which makes sense because your output is going to be some continuous, it's a continuous function. So you need numbers essentially for it to work. So we're going to use something called an encoder, and all this does is that it's converting those binary variables into zeros and ones. So that way your algorithm can actually work with it. So in this case, after I apply the encoder to those columns, if you look again, you can see that it changed to ones and zeros. So the next part of this is going to be our training and testing data. So like I said earlier, it's important to split your data set so that you have, you can save some of the data for it to be tested on. Typically, you can go like an 80-20 or 70-20 split. You typically want to feed more of that data into your training, and then testing can typically be a smaller subset of that. So in this case, I set training to 70% of the data, and testing is set to 30%. And then this random state here, all it's ensuring is that if you pick the same random state, that you can get reproducible data. And reproducibility is also another important thing. So if you want to look at your results and then kind of analyze and see where you might go wrong, if you don't choose a random state, it's really hard to reproduce those, reproduce your output. So again, it's important if you want to be able to like look back at it and really analyze it. So after I ran the train test split, and this is just a function that's already part of scikit-learn, but you can see that it went from what, 545 records to 381. So we've split, this is the 70% split for training. And then you can see that our testing data is 164 records. So that's our, that's the 30% split. So, and as you can see too, if you look at it, it splits it randomly. Like it's not like it takes the first 70% of the data and then the next 30%. That's again due to that random state. So just a heads up, it's not like in order. Okay, next is data scaling. So, and this isn't something you're gonna always have to do, but in this case, if you want all of your features to have the same effect on your output, you want them to be on the same magnitude. So this is so that it's not like any of one of our features, just because it tends to have bigger numbers, bigger magnitude, that it's going to have more effect. So if you look back at our data, you can see that typically all of our features are ranging from like 0 to 5. Meanwhile, like areas like in the thousands. So something we do here is scale that data down to be on that same magnitude as the rest of it. So in this case, we scale all of our data points, and we use just, again, min-max scaler. This is part of the scikit library, and it will do it for you. So make sure you apply that scaling to both your training and testing data too. This is also something you can do before you split them, but I just happened to do it in this order. Okay. So now for training the model. So in this case, first thing I do here is I give it our label. So this is going to be what's on our y-axis. That's weird. Okay, yeah, so this is going to be on our y-axis. So this is going to be the price. And then everything else is our feature variables. So I separate those two from my training data. And then right here, I'm just creating an instance of a linear regression model. And so I then go and fit that to our training data. So here you can see that it made that instance, and it's fitted to our training data. And then same thing, now I need to give it the predictions. So I want to see how well my model does. So make sure that you don't want to give it the labels because that's what it's trying to predict. So I remove this data test.popPrice. All it's doing is it's removing that price column so that it can actually just look at the features and then go based off that. So when you do your prediction, again, you're only feeding it that feature data, so it doesn't actually know what it's supposed to be. So after training and testing, you can then go into like model performance. And there's a lot of different ways you can essentially test how well your model does. There's a lot of different metrics. In our case, we're just using mean squared error and our R-squared values. So for mean squared error, that's just essentially telling you how well, how far away from the mean that your predictions are. So oh, I didn't separate these, and then meanwhile, our R-squared, or coefficient of determination, tells you how well the model is fitting the actual data, and how much of that variation is being explained by your features. So if we actually run these, and they're already ran, the cell's already run, you can see that these are actually pretty high right here. This is not like good. This is really high. So for our mean squared error, and then root mean square error, this does it in the actual magnitude of what you're trying to predict. So in this case, since we're predicting price, we're off by about it's like $1 million. That's not that's not a good model. So don't worry, I'm gonna go into how we can fix this, but like I said, this was like our first pass over this, so you're never really gonna get it right on the first try, but if we look at our R-squared data, it's like 0.64. That means like 64% of that variation is being explained by our features, which isn't bad. It's more than half, but like, again, that could always be better. So here I actually even plot it. So this is our actual values against our prediction. And typically what you want to see, if you want to see like a straight diagonal going across this plot, and like the further away those points are from that line means like that's more of your variation that you're seeing. And then this is our residuals here. And that's, again, shows you how much variation there is within your errors. And it's typically you want this to be random along this dotted line, that's 0. So because you can see that it's kind of going in like diagonal, that typically means I'm over predicting on the higher up I go and then under predicting the lower a value is. You typically want this to be randomized around 0. So what are some ways we can fix this? So there's a lot of different ways. So like I said, if you look back at how many features we're looking at, we're only looking at like, what is this, like 9, 8 features? For some cases, this might be too little, and for some cases, this might be too many. So maybe what it is that we need to find new features that we can look at, or we want to do some kind of feature engineering where we're combining some of these features together to get something that's, to get data that's more contextualized, that's more important to our model. Another thing might be that we just need to regularize it. So we can do some kind of regularization on this to prevent any kind of over or underfitting. I don't want to get too much into the math behind that. Another thing we can do is that maybe this just isn't the right model to use for this kind of problem. So like I said, there's lots of different kinds of models out there. Maybe linear regression isn't the best one for this. Maybe we should be trying some kind of like binary tree, or maybe we should be trying some other kinds of models. It could also just be a data issue. Like we only had, what, 500 something records? Maybe this is something you want to get more information on. Maybe you want something in the thousands of records to kind of better inform your model. But it could also just be how we're evaluating the metrics. So something to think about is what kind of metrics are appropriate for your model when you're trying to evaluate how well it did. And that can come down to a lot of different things. So for example, I personally didn't check the distribution of my data. Maybe my data just tends to have like a lot of really like low priced houses and a lot of really high priced houses, but nothing in the middle. And so that's something else to keep in mind, is how balanced is your data set. So if your data set isn't balanced, maybe you shouldn't be looking at like accuracy to see how well your model did. Yeah, I think there's a lot of other ways we can go about it, kind of going back to this. Well, actually, does anyone have any questions about anything that I just showed on the model? No? Okay, cool. So I am going through this very fast. I apologize. But something to think, yes? My favorite model? I don't know. I like support vector machines. Yeah.
I actually am kind of curious. Like, I don't really understand how support vector machines work.
Okay, so it's easier to think about it in like 2 dimensions, I'd say, because the higher up you go, you have hyperplanes, and it's kind of hard to see what direction this is going. But imagine you have like it typically works for binary classification. If you're trying to see two different classes, and actually let me just pull up a picture of. Yeah. So, like, let's say you have your data is like, you have two very distinct like groups of data. What you're trying to do is you're trying to find the plane that is able to separate that data the most efficiently. So this is a really clean example because you don't see the data crossing this line at all, but sometimes you'll have it where that boundary gets really close to each other, where like you can see some of the data is mixed on each other. And like, sometimes that has to happen because if you don't find a place where you can maximize that margin of your plane, then you're gonna have overfitting. But typically all you're trying to do is find like where that plane goes through to separate your data. And the great thing with support vector machines is that it's also not linear. You have these things called kernels that basically allow you to like delineate your data if it's not linear. So you can have
Donuts.
Yeah, like is that RBF or?
I think so. Like, depending on the manifold that you're working on.
Yeah, so sometimes your data isn't like, can't be separated by a straight plane. Sometimes you need, like donuts if it's like in on itself. Sometimes if you need like just more flexibility with your plane, it can kind of curve around it. But yeah, and this is what I was talking about. Like once you start going up to dimensions, like it becomes a plane. It's not like a straight line anymore. So yeah, does that kind of answer your question?
Yeah, I'd like to know more about the math stuff.
That's I feel like it's a lot to talk about with this. But like where I was going with this with like further learning is that honestly I think you don't have to be amazing at math to understand machine learning, but you should know some of the principles behind it, because then at that point you're just plugging functions in and just kind of, I don't know, hoping for the best. It helps you, especially if you want to fine-tune your model. It kind of gives you direction into how you should be going about it versus just kind of trying random things and hoping it fixes it. So in this case, linear algebra, again, there's a lot of concepts from linear algebra that you're going to find in machine learning that make it pretty prominent. Probability and statistics, again, this is a good one to have. And then also some basic calculus, especially if you're moving into like neural networks, it's important to know about a little bit of calculus. I think the classes here don't necessarily go that deep into the math, but they definitely do teach some of the concepts so you understand like gradient descent or something like that. Like I said, another one is going to be data cleaning. So, because again, if you're getting your data from a lot of different places, especially or a lot of like web scraping or like any organic data that's not already like formatted by anyone, it's gonna be kind of hard to work with. Like personally, I'm working on a deep learning project with satellite imagery, and I'm having to manually go in and kind of look at the images I'm getting because there's a lot of cloud cover and it's not something that I can use in my model. So I'm trying to like cut out pieces of it that I can actually use for my project, which is a little tedious, but thankfully it's only a couple photos, so it's not taking me forever. And then some other like libraries you want to get familiar with, especially like TensorFlow and PyTorch. There's like a lot that goes behind these libraries, so there's a lot of material to learn. And then like I said, for data sets, Kaggle is a really good place to go and just kind of explore what's there for you to learn. And then here, since we still have time, I'll show you guys, this one website. This allows you to kind of understand neural networks a little bit better without you having to actually code it yourself. You can just mess with the different kinds of parameters and hyperparameters to see what happens when you have different kinds of data. So I like this website. It's really good if you just kind of want to understand some of the math behind it to understand like how like our delineation is going. There's another website that I learned in class that's also kind of like this neural network playground, but it's for like generative adversarial networks. I wish I could remember what it was called, but I learned about it, and it's yeah, it's also, there's like, if you don't want to go out of your way to like code these by hand to just kind of understand intuitively what's happening, there's a lot of like different playgrounds out there that kind of have it pre-coded where you can mess with the inputs and then see what's happening. So yeah. I don't know, are there any more questions?
Which courses you're like focus more on becoming a machine learning engineer. Of course, this year at UTSA and the CS program, the CS or the math department, which are those two.
So currently I've taken data science, machine learning, and I'm currently in deep learning right now. I'd say that's kind of hard. Because I will say, what I've learned with the classes here is that if you want to kind of learn explicitly how to code these things, they're not going to teach you that outright. What they teach you is the theory behind it. And then, like in my classes, we've just had like term-long projects that's where we do all of our coding essentially. And then class lecture time is specifically just for learning about the concepts. So I honestly really enjoy the machine learning and the deep learning course here. I think it's really informative. Even if you don't, again, explicitly learn how to code it, I think I've learned a lot with the theory behind it. I can't say anything about the math classes. I'm in optimization right now, which helps a little bit, but it... Yeah, go ahead.
Sorry. So yeah, optimization, the optimization class is really on finite dimensional stuff, which is good because we like finite dimensional stuff. We like RM. It's just, once you start talking about other things, you get some more, but that's a good start. Probability and computing, I really strongly suggest going through really talking about like randomized algorithms, because that tells you like how some of these gradient descent things are really improved. There's a new course that's being piloted now, a new graduate course called Algorithmic Foundations for Data Science. It's currently processed as math and CS, but we're trying to get it as a full course. And for some of the other foundations too, like they'll kind of get you started, like apply linear algebra or any linear algebra class, because everything is a matrix / tensor. More math, like numerical analysis, will get you there to understand how these algorithms work, how you can like improve, when these things make sense to use. And a bunch of stat classes too, honestly. Everyone should take a stat class.
Honestly, yeah. I think if I had more time here at UTSA, I would definitely take more of the math classes, but it's my last semester, so you take what you can get. But I don't know, are there any other questions? Again, like I said, I'm sorry, I know I went through that really fast, but if there's anything you guys want me to go over again.
I mean, if you have time, you feel for like gradient descent a little bit.
I don't know if I want to like just kind of like rock down gradient descent right now. I'm like.
There's like a
What's the boilerplate gradient descent?
So you are trying to minimize your loss function in gradient descent, and essentially you are trying to move down that gradient to find where that minimizes the most, and that works really well for like convex algorithms. The more varied it gets, the harder it is to get down to your optimal minimum.
You have a whiteboard.
I don't want to direct gradient descent. Actually, Jake, why don't you direct gradient descent?
Yeah, I've seen like 3 of the lectures. I learned everything from the internet.
You're trying to climb that mountain.
Yeah. Okay, yeah, sure, I'll draw. Wait, who has a...
I have like a
Because, like, essentially, if you have a complex function that's like this, and you're trying to get down here at your optimal point, you're just trying to move down this gradient. So, again, like, there's a little bit of calculus here. You're trying to take the derivative of your function and move down it. But, like, if you have a function that looks like this, it's really easy to get stuck in one of these two. These are called local minimums, but this is your global minimum right here. So you can get stuck, like, here, or you can get stuck here. So there's different ways you can smooth your function out, like different transformations you can apply so that you can get it looking like this, especially with some of your neural networks. There's ways you can apply that, but I think I remember that. Yeah.
What do you mean by stuck?
So, like, if you take, can you take the derivative of, like, 0, essentially?
I mean, you can. It just gives you
Yeah, so that means you can't keep moving down.
Okay.
That means your derivative gets stuck here, and you can't keep moving down this side. So that's what I mean by stuff.
When Sean was kind of talking about like the randomized algorithm, sometimes it's helpful to kind of give that gradient descent algorithm a little like I'll call it like jitter, kind of have it add some like randomized value to it so that it doesn't getting like stuck here. It might get a little extra like randomized bump and it might push it over that edge. basically
Momentum is also another way.
Momentum
Like
is
the
Yeah.
heavy ball analogy, like you basically are at the local minimum, then roller coasters like
Yeah, like if your step size gets really big, you can surpass that local minimum, and it also just largely depends on starting point too. Then your function, there's a lot of research into like just start algorithms in general. So that is also something. Like I said, there's a lot of math that goes into this. So I know like I don't know. I personally didn't really like math a lot, but like the more that I got interested in this, the more that I wanted to learn what went into it. So I don't know. I think is there any other? I think I'll end it here then. Okay, cool. Oh wait, hold on.
Thank you again, Clarice, for doing the machine learning. And since this is our last intro to tech, we are open to new ideas. I'm turning my microphone. We are open to new ideas for the next semester. So if you have anything that like you think should be covered in intro to tech, scan this QR code and fill out this form. Be going over it over the summer and just picking out some ideas that we seem interesting. You do not have to keep it to beginner-friendly ideas. We are working on like other ideas, maybe other series for more advanced topics, maybe that you want to see covered. Stuff that you think like everyone should know about, basic concepts. Again, scan this QR code to submit your ideas, and we'll go through and maybe pick the best ones we see. We might be able to have a schedule out for almost every intro to tech by open house next semester. Who knows if you'll have a bunch of ideas. But again, thank you, Clarice, for machine learning workshop, and again, thank you all for coming.